graphs of the trig functions. There's a lot of useful information we can access if we graph sine, cos, or tan of the angle over the angle, by which I mean on the x-axis, our x-axis graphs theta, the angle. The y-axis, we graph sine of the angle or cos of the angle, and we can also graph tan of the angle, tan theta, but we won't do so for this exercise. It's interesting to have a look at it though. Now what I mean by this, and I'm just skipping ahead for a moment, is this graph here. When the angle is 0 degrees, cos of the angle is 1. This is actually incorrect on your worksheet. They've got 0. Please replace it with 1. X-axis shows theta in increments of 30 degrees here. The y-axis shows the value of cos theta. When theta is 0, cos theta, cos of 0 is 1. Now, it's a really good idea to have a look at the interactive unit circle in order to do this, and I'll have a look at that later if you'd like. But here's the first question we've got to tackle. Complete the value, the table for sine of the angle, sine theta. Now you can refer to the unit circle. So sine of 30 degrees, sine is the the y value, and that's 0.5. Or you can just use your calculator. We also know exact values, but we might as well just use the calculator. Sine of 60, 0.87. Sine of 90 degrees, we know that one, it's 1. Sine of 120 is done. Sine of 150, it's a half. And sine of 180, we know this one, that's going to be 0. Checking with the calculator is fine. So sine of 240, negative, 0.87. Sine of 270, negative 1. Sine of 300, negative 0.87. Sine of 330, and we know that 360 is going to be 0. So it's a little bit messy to fit that in. What they're asking when they want us to graph those points, which I did down here before for the cos of the angle, is we're graphing y equals sine theta. So the line that turns up is the line of y equals sine theta. When theta is 0, sine theta is 0. When theta is 30, sine theta is 0.5. When theta is 60, sine theta is 0.87. When theta is 90, sine theta is 1. 120. So you can see that we've got a very symmetrical, very easy to plot set of points that makes this really beautiful curve. And join it with a very smooth curve as accurately as you can. So, sorry, I'd normally turn my page around to do that. We also usually suggest graphing in pencil, but it doesn't turn up easily. So this is the graph of y equals sine theta. It is not, the y and the x are not to be confused with the coordinates x and y of point P on the unit circle. So when I say down here, I have the graph of y equals cos theta, don't go saying, wait up, but cos theta equals x. That's completely different. That is, on the unit circle, sine theta equals the y-coordinate of point P, and cos theta equals the x-coordinate of point P. That is different. Here we are graphing the value of sine theta over the value of theta, and the value of cos theta over the value of theta. You'll notice they're similarly shaped, just offset by where they start at 0. A couple of terms about the graphs. The period for each of these is 360 degrees, and the period of any wave function or curve is the time it takes to do one full cycle. Up, down, and up again. That's one full cycle of this graph, one full cycle of the cos graph. The amplitude is 1 for both of these, and that's the maximum distance from the x-axis in absolute values. So it's 1 away, it's 1 away, it's not +1 -1. Quite obviously, the quadrants of the unit circle can be clearly seen on our graph. Up to 90 is quadrant 1. 90 to 180 is quadrant 2, quadrant 3, quadrant 4. And you could put little dashed lines, if you could draw a straight line, my goodness. You could put little dashed lines through it. And that can be quite helpful because you can see approximately the value of sine of the angle in quadrant 1, quadrant 2, quadrant 3, quadrant 4. As we know from all stations to central, sine is going to be positive in the first two quadrants. Sine of the angle is positive in the first two, negative in the last two. Cos is going to be positive in the first and fourth quadrant. First quadrant and fourth quadrant. So it's really quite useful. Please remember also that we can go over 360, and you can predict sine of 390 degrees will follow this pattern. It's going to be 0.5. We can check with the calculator. Sine of 390 is 0.5. So this can keep on going for larger angles, and please do have a look at the unit circle for how this graph works. So the types of questions that we might use this for. Use the graph of y equals cos theta to estimate the value of cos theta when theta equals 200. So we have theta, 180, 200 is about here, and the value of theta looks like it will be around about negative 0.9. If we wanted to check that with the calculator, cos 200, about negative 0.9. So that's cos theta equals approximately negative 0.9. Estimate the two values of theta for which cos theta equals 0.7. Cos theta is 0.7, so around about here. You could use a ruler if you wanted. There's one spot, and there's the other. So we're estimating this value of theta and this value of theta. Each of these is 30, so that looks like around about 45 degrees. 315 degrees-ish. Remember, you want your little approximately equals. And of course, if cos theta is 0.7, inverse cos 0.7 about 45 degrees. Why do we get the 315? Because, of course, we're looking at reference values in this quadrant here. We may also want to use the graphs instead of the unit circle to remember whether sine, cos, and tan should be positive or negative. So use the graphs to state whether sine 120 and sine 210 should be positive or negative. So you go to your graph, 120, sine should be positive. 210, sine should be negative. We're looking for where the line is of the graph. Cos 120, cos should be negative. Cos of 340 should be positive. So it's often easier to use the graphs to work out whether something should be positive or negative based on the quadrants and the size of the angle, compared to using that on the unit circle. It's up to you which you find easier.